Today we are going to talk about tangents some more. So yesterday we defined tangents. Somebody remind me, what is a tangent to a circle?
It is a line that touches the circle in one spot.
It is a line that touches the circle in exactly one spot. That was a perfect definition. So today we're going to talk more about tangents. So we're going to begin with a theorem about tangents. It says, if a line is drawn tangent to a circle, then the line is perpendicular. What does perpendicular mean?
That's at 90 degrees.
Hits at 90 degrees to the radius. What is a radius?
Half the diameter.
Half the diameter, or a segment that goes from where to where?
The center point to the circumference.
The center to the edge. To the point of tangency. That was another vocabulary yesterday. What was the point of tangency? The point the tangent touches the circle. Okay, so here's my point of tangency. Drawn my center. A radius goes center to edge. And according to this theorem, that's going to create a right angle. Okay, so if I have a tangent line and I connect where that tangent hits the circle to the center, drawing in a radius, that radius will be perpendicular to the tangent line according to that theorem. A corollary to that says that if I have a circle, and to that circle I draw more than one tangent from a point that is outside of the circle. So if I draw in a tangent above and a tangent below, this is the corollary. From that point where they intersect to their points of tangency, those two lengths will be congruent. So if I have two tangents that intersect outside of a circle, the length from where they intersect to where each of them meets the circle is equivalent or congruent. Theorem 9.2. If a line in the plane of a circle is perpendicular to the radius at its endpoint. Well, that looks a whole lot like the picture we already drew for Theorem 9.1. It says then that line happens to be a tangent. Theorem 9.1 and 9.2 say the same thing but backwards. What do we call that? Converse. Converse is where they say the same thing but backwards. So the picture would be the same. It's just a matter of what we're given. So if I know I have a tangent, then I can know that it is perpendicular to the radius. If I know I have a perpendicular line to a radius, that must mean that line is a tangent. So Theorem 9.2 and Theorem 9.1 have the same picture, the same diagram. It's just a matter of what we're starting with. Are we starting with knowledge that we have a tangent? We can conclude it's perpendicular then. Or are we starting with information that it's perpendicular? We could conclude that it is a tangent then. Some more terms. Yesterday, we talked about taking a circle and drawing inside of that circle different shapes. Our first term here says the opposite, that we're going to put the polygon or the shape circumscribed or outside of the circle. So I'm going to have a circle, and outside of that, I'm going to have a shape such that each one of the sides of that shape is tangent to the circle. I drew it here with a square. We could also do this with triangles or pentagons or any number side of figure. So we learned the terms yesterday, inscribed and circumscribed. So just remember that circumscribed means outside. So if I was describing this picture, the thing that is outside is the polygon. So the polygon is doing the circumscribing. Inscribed means inside. So in this picture, the circle is inscribed because the circle is the inside part. Okay, circumscribed is the outside part. Inscribed is the inside part. Our next term says common tangent. For a common tangent, we are going to have more than one circle. And a common tangent is a line that is a line that is tangent to both of the circles. So a common tangent is a single line that is tangent to more than one circle. Then we get more specific here and give it another descriptor of either being internal or external. A common internal tangent, it says, intersects the segment that joins the circle's centers. So if I take their centers and connect those, if that common tangent crosses that line, it's called internal. This one does not cross that line. So our next term says external, that it doesn't intersect. So this would be an external tangent. Whereas an internal tangent would go between the circles, cutting that line that connects their centers. The final term here is tangent circles, and that would be two circles that are tangent to each other. So two circles that just brush along each other at one point. Questions on any of our new vocabulary? All right, so I have several diagrams here. We're going to think about these internal, external, common tangents. Wrong button. Let's get back to the diagrams. So in the first one, upper left, how many common external tangents could I draw? 2. If I'm thinking external, I could have one that goes along the top, one that goes along the bottom. I'd get 2 externals. What about top center? 2. Again, one along the top, one along the bottom. Oops, I kind of cut in there. Pretend. And top right? 2 again. Bottom left? 2. Okay, we're starting to see a pattern here. Bottom center? 1. What would it look like?
On the side of the circle.
Along the side of the circle where the two circles meet, we'll have a line meeting as well. Now, how do you know that that's external and not internal?
It doesn't go in between it into central points.
Our definition says that it has to do with the center points. So if I draw in those center points and I connect those centers, this tangent line does not cross that line that connects their centers. So by definition, that means that it's external. And the final one, how many external common tangents there? 0. What would we call those two circles? Definition from yesterday. Concentric. They have the same center. So that's our bullseye picture, concentric. Okay, let's go through these same pictures again, but now think about internals. So, upper left, how many common internal tangents?
1.
Here, lots of ones. Can anybody raise the ante? Come up with another one?
2.
How would I draw them if there's 2 and not 1?
Like an X.
They'd make an X. So I could have one that comes like this, and one that comes in like that. And that would cross the line that connects their centers. So we get 2 internals there. What about top center?
Just
Could you
one.
put one down the middle? Yeah.
Yes, I could have one that's going to go right down the middle there. And that's internal because it crosses the centers. Since lines have no thickness, even though those two circles are touching, we can still kind of squeeze that line between there because lines don't have a thickness. What about top right? None. There's no way to draw a tangent that's going to cross through those centers, through the line connecting the centers? Bottom left? None. Bottom center? None. The only tangent is the one that we drew, which was external. And bottom right?
You can go right through the center.
If I go right through the center, I'm not actually going to touch either circles, right? So, I mean, I could go like that, but that's not a tangent, because a tangent's supposed to just touch at one point. So there's no way to touch at just one point. So we don't end up with any there either. So we can see here from this that external tangents are a lot more popular or easier to come by than internal tangents. I wanted to find two new terms that were not on our sheet, but I think you can probably figure out what they mean. I want to know, of these 6 diagrams, in which one would you say that the circles are externally tangent to each other? Okay, so we talked about what it means for circles to be tangent to each other. If 2 circles are tangent to each other, what does that mean? They touch in one spot. So if I want them to be externally tangent, what would that look like? Which one of these? The middle on the top. They are tangent to each other, and they are outside of each other. So they'd be externally tangent. What about then internally tangent? Bottom middle. They are still tangent to each other, but one of them is inside of the other one. So they are internally tangent. For your homework tonight, I have this kind of crazy belief that you should remember some things that you've been taught before. So this lesson will have a lot of review ideas in it that you will need to remember. So the first thing that you will need to remember is that when we have a right triangle, and I know how long 2 sides of it are, I can find out how long that third side of it is. How can I do that? A squared plus B squared equals C squared in general. If it happens to be a 30, 60, 90, or 45, 45, 90, then we can apply some special patterns. But if we don't know for sure that it is one of those special patterns, we can still do Pythagorean theorem. A squared plus B squared equals C squared. So you will need to use Pythagorean theorem on some of your questions tonight. On number 8, you do not need to do part D of the question. It's an ABCD question. You do not need to do part D on number 8. On number 10, you are going to need to remember the idea of geometric mean, which we studied in lesson 8.1. And that picture was given by this, where we have our stacked right triangles and we could figure out how big different pieces were. So in number 10, you will need to go back to the idea of geometric mean. If you are feeling a little dusty on that, you will go back to section 8.1 or your chapter 8 test and look over that idea. And on number 16, number 16 deals with similar triangles, which was back in chapter 7 where we studied proportions. So if you are feeling dusty on that, go back to chapter 7 and look at how to solve proportions and cross multiply.